Okay, welcome everyone to this joint SRP AURPO webinar. This one is on radiation risk assessment. Next slide, please, Charlene. As you can see, we have an awful lot of registrants for this webinar. That's a fantastic number, over 700 of you registered for this event. That again demonstrates just how useful these events are proving to be. Of course, we want you to be able to ask questions, and the best way to do that is to ask those questions through the Q&A box, which is should be available somewhere on your screen during this webinar. Obviously, we won't necessarily be able to get through all the questions, but we will certainly try to triage them and answer the most liked questions, as it were, the most significant questions that are answered live. All other questions will be followed up and answered afterwards through and available as answers on the SRP's website. If you want to claim CPD points as registering your attendance, you just need to email the code that's given there, R*8RA, to the SRP email address that's on your screen now. You will be able to then use that register of attendance to claim CPD. As with all events like this, we continue to learn through running them, and I please do ask you to give us your feedback. There will be an emailed online survey link available after the webinar. Do give us the feedback so that we can, of course, improve, make these events better in future. Next slide, please. We have further webinars planned. We started this webinar program about a year ago, and we thought it would run for a certain amount of time, and we would see how it worked and rate its successes, as it were. It is patently obvious that it is a wonderful resource, irrespective of the restrictions that we have on face-to-face during lockdown, and so we will continue to run them. So there are 2 more coming up in May, and we will have a program going in through the summer into the autumn. So if you do have your own suggestions for webinars, please do email the admin office at SRP. Obviously, we want to encourage more of you, if you're not currently members of SRP, to join. We have the journal. It's actually free with membership of SRP. We also have a weekly e-newsletter, and we are shortly to launch a magazine as well. That does offer you a range of benefits, and so I would encourage you to, at the very least, look at the website and consider the benefits of joining the society. I think that's it, unless there's anything else on the slides. Yes, of course. One other thing to encourage you to consider, if you are already a member, not just of SRP, but IPM, you can, through your membership, you can apply for chartered radiation protection professional status if you are experienced in radiation protection. But there are more recently new and more appropriate levels of recognition for those who are perhaps more junior or earlier in their careers. So please do look at the information that's on the SRP website for IRADP, TechRADP, as well as chartered status. I think we are intending to improve the pages on that, because I think there's a lot of benefits of having that individual recognition, and we haven't really set it out in as much detail as we should on the website. So do consider professional registration. Anything else? Right, well, I'm going to firstly say a big thank you to the speaker today for agreeing to give this talk on risk assessment. But the next thing I ought to do is to actually introduce Pete Cole, who is the current president of AURPO, who's actually going to formally introduce our speaker for this webinar. So Pete, over to you.
Thanks, Jim. Hello, everyone. Good afternoon. I'd just like to reiterate some of the things that Jim's just said. I'm delighted to be here again for another webinar. and I'm delighted that AURPO and SRP are collaborating in this endeavour, which is absolutely fantastic, as Jim says, providing training opportunities in these difficult times, not only for our memberships, but also for the whole worldwide radiation protection community. So without further ado, I will begin to introduce our speaker today, Mark Bradley from STFC. After leaving university, Mark went to the NRPB, where he received rigorous training in all things radiation protection. 8 years on, he moved to the Health and Safety Executive to become a specialist radiation inspector. Subsequently, he achieved his formal RPA certification and RWA certification. And after HSE, he became the RPA RWA at Oxford University, where he spent a lovely 12 years. Mark's latest move has been to join the RPA team at STFC in Harwell. I am absolutely delighted to say again that Mark is the current chair of the AURPO Scientific and Technical Committee. So, having said all that, over to you, Mark. Thank you.
Thank you, Peter. If you can all bear with me, I'm going to be wearing ear defenders for this talk. I'm at home, so I'm cutting out the ambient noise from my neighbourhood. So 2 seconds. Okay, thank you for Peter. Jim, thanks to AURPO and SRP for asking me to speak. 700 people. If I was nervous before, I certainly am now. It's higher than the average attendance at a Premier League gate this season, it would appear. Just to say something that's been playing on my mind, it's a recurring nightmare of mine to stand in front of a lecture theatre and realise you haven't put your trousers on. Seems today that your dreams can come true. So, what's today's talk about? Well, today's talk is all about the application of IRR 17, Regulation 8 on risk assessment and its accompanying ACOP and guidance. It's going to be a practical talk. It's going to be targeted at those who are at the start of their radiation protection career. I'm going to be sharing opinions, though, that hopefully of interest to all. So if you're an experienced risk assessor, you might get something new out of it. It's an overview of the process and the pitfalls of radiation risk assessment. Because it's a long 3 words, I'll shorten it to RRA, and it's all based on my practical experience. So first off, why do we do risk assessment? Is compliance your sole motive? Or is it to help you identify robust and proportionate controls? The end point of any suitable and sufficient risk assessment should be a LARP. So this is providing you some reassurance and justification for your decisions on radiation. One thing you have to be clear about when you start an RRA is what you intend to get out of the process. Radiation protection lends itself to mathematics, and it's easy to get drawn into complicated exposure scenarios, dose estimates that come up with a number, but by the time you've got to that number, you've really forgotten why you were going there in the first place, and what does that number actually tell you anything. And you've got to be careful with your numbers anyway, because calculations and dose estimates in risk assessment are prone to error. Assuming an isotope dominates for everything, for example, assuming the inverse square law to situations that don't suit it. So you have to really be careful with numbers. And at the other end of the spectrum, other than on a risk assessment training course, I've never in my life multiplied 2 numbers together to help me understand how risky work with ionizing radiation is based on what primary colour I land on. I'm not really a great fan of the kind of risk assessment you see in that image there. In the risk assessment process, in most situations, we can just make sensible judgments about whether something that's somewhere between possible and probable carries a significant risk of exposure. In the risk assessment process, we're just really talking about things that are somewhere between possible and probable, and whether you whether there's a risk of receiving a significant exposure out of something happens. For example, if I don't do something to restrict access into an area, could somebody walk in and receive millisieverts in no time at all? If so, how difficult is it to fix? Is there a better way to fix it? And does fixing it create additional problems that you then have to go on and solve? So there's lots of considerations. Like I say, it's all going to be practical. I'm not going to go into great detail about risk coefficients, risk factors, all of that kind of stuff. It's going to be practical considerations of doing risk assessments. So lots to say, let's crack on. Risk assessment as a concept was formally introduced into UK legislation in the management regs in '92. There was a HSE 5-step approach that people are probably well familiar with, shown there in the image on the right. Identify the hazards or the risk factors, identify who could be harmed and how they could be harmed, evaluate the risks, look at the measures you've got to control those risks, considering the hierarchy of control measures, engineering controls, safety features and warning devices, and then personal protective equipment, procedural controls, and then finally record and review that risk assessment. Before then, the IRRs, the 85 regs, were prescriptive. There were schedules of reference values that prompted some action. And there was almost a secondary consideration that you do a hazard assessment, but that came in the legislation after the local rules. So you could sit down and write a set of procedures, a set of local rules, your safety instructions that followed a format. And when you got to the contingency plans, as for example, you'd roll out the same ones: loss, theft, fire, X-ray set fails to terminate, somebody thinks they've got an exposure. And you'd write those in your local rules, whether or not you truly believed any of the initial events that would lead to you needing to use them were actually ever likely. So in the 99 IRRs, risk assessment for radiation protection came into place. So risk assessment was effectively introduced to a new audience, but it put risk assessment at the core of the regulations. They became the spine there. If you did a risk assessment properly, everything fell out of it. And it was at about that time I became a regulator. That's when I joined HSE at the dawn of the 99 regs. And it could become the first question if you saw something that wasn't quite right. So you'd go into a premises, if something looked a bit odd, you could say, okay, what does your risk assessment say about this? And I'll give you for example. Here we've got a schematic showing a transport hub depot that I visited in the early 2000s. It was for a preventive inspection. I visited during the daytime. This was a kind of premises that receives lots of radioactive materials from airports. Then it reorganizes them into onto individual pallets, which are then separated out and driven around the country. The daytime visit identified some issues. You can see on that slide there, that store where the radioactive materials are being kept looks sort of like a radiography enclosure, and that's because it sort of was a radiography enclosure. It had doors at the front, but it had a maze entrance at the back, so the materials were never secure. So I swore to return. And I swore to return during the night time because most of their work was done in the night time. And when I went back, there were obviously some more significant issues. So this is what happened on my nighttime visit. You can see there they'd blocked up the maze entrance at the back, so that was good news. But there were an awful lot more radioactive materials lying around the depot. They'd locked the doors. Absolutely great. So it seemed that they'd acted on most of our advice. But had they? They'd locked the doors together, but you could still slide them. Okay, they were a bit of a heavier door, and they were one door rather than two, but you could slide them apart, and so there was still no physical restriction of access. And they were also storing high hazard packages. So this is an example of one of the packages, and this is an example of how they were storing them. And that had significant consequences on the people sharing the adjacent office. So there we have a situation where there were lots of things wrong. The high dose rates in the office, as a for example, could have been identified. The office was where they stored their unworn dose meters. They stored the spare dose meters. And if you looked at the dose records for those spare dose meters, they were getting above classification thresholds. So there was no structure at all to their safety thinking. The company were dismissive of the significance. They actually came out fighting and they got themselves into quite a lot of trouble in the end. But all of those things are identifiable, and the risk assessment process in the IRRs enables you to go through them in a structured way. Now, some basics. I realise we've got to this point and I haven't made sure we all know what we're talking about. So here are some definitions. So the first one, what's a hazard? Well, here we've got the concise Oxford definition. And if you look at the definition of hazard there, hazard is the thing that can do you harm. And we're talking today about the hazard being ionizing radiation. Now, it's a bit disappointing that in this edition of the concise Oxford, in the 99 edition, they wouldn't have tried particularly hard to get the definition right. If you also look at risk, risk is the probability, the likelihood, the potential that that hazard could lead you to being harmed. So when we're talking about risk assessment, or when I'm talking about risk assessment to you today, I'm talking about the risk of significant exposure. For work with ionizing radiation, the risk is accounted for in dose limits, in reference levels embedded in the regulations. For example, in the latest regs, risk is factored into the graded approach for notification, registrations and consents. In our slide there, just to identify hazards we're talking about. So the hazards in that slide there would be our ice, the hazard would be the banana, and the risk would be that the penguin slips over and hurts himself. So what do the regs say about risk assessment? Well, the regs say you do a risk assessment. So you do a risk assessment that identifies all the significant risks and how big they are. And they say that if you can identify any accidents, then you do the best you can to stop them happening or to take actions to limit the consequences. And then based on the outcome, you provide information, instruction and training to people who need it. Now, if you're familiar with the ionizing radiations regs or UK legislation, you're familiar with the structure of them, and you've got regulations, you've got AURPO, and you've got guidance notes. And in the case of risk assessment, the AURPO is incredibly useful. There are two sections in there, and one is what to consider and one is what to conclude. And these sections effectively hold your hand through the big decisions on your major control measures to satisfy IRRs. If you follow the template, you can argue to HSE that your risk assessment is going to be suitable and sufficient. And by the time you've got to the end of it, the end point of your risk assessment should be that you can argue you're satisfying a LARP. If you look at that little image in the slide, and I've included at various points in my talk, I've included things that appear to be documents pasted into the side just to show you what they are. I'm not suggesting you read through them. I'm not going to read through them as part of the talk. You can just glance at them if you like, and you can look at them in the slides afterwards. But effectively, there's a slot from section AURPO section 70, and that says these are the things that you should consider when you're doing your risk assessment. So it's a structured approach to considering all aspects related to the hazard, how you can be faced with a hazard, and then AURPO 71, what do you conclude as a result of it? But is IRR 17 enough? Does the AURPO do enough about risk assessment? Well, if you go back to what HSE is saying, the 5-step approach to risk assessment, you've got who could be harmed and how. So if you just follow the sort of the prescriptive statements in AURPO 70 and 71, you've perhaps not gone far enough. So if all you have is an AURPO based radiation risk assessment, you might have to top and tail it with additional information related to the personnel and how they interact with the source. And what about the other specific aspects of risk assessment? Well, a risk assessment should enable you to identify the other legislative controls that are relevant. So, for example, is my inventory big enough that rep here comes into play? What about optimization of waste management and BAT? Now, whilst they might not feature in the actual risk assessment, and for BAT it's sensible that it doesn't, but your risk assessment should point you in the direction of needing to do or to address these other regulatory requirements. So practically then, does every risk assessment need to look the same? Well, I see the risk assessments as being three different types of thing. A main radiation risk assessment, my view on it, is that it's a way of considering all aspects of compliance with the regulations for your work activity. So, for example, if a new employer sets up for the first time to do work with radiation, if you go through the risk assessment process in IRRs, they effectively hold your hands through holistically complying with the regulations. You see there on our image, that's an image of the Rutherford site. The highlighted area is our ISIS accelerator facility. And what you see at the bottom there is a summary document. And it is a summary document. The main risk assessment for such a facility is absolutely massive, but it's a summary document that takes you through what AURPO 70 and 71 say. So the outcome of that risk assessment is that we know that the measures we have in place are sufficient to comply with the regs for the accelerator. Then you have to accept that there are other things that you might want to risk assess in different ways. And the next one I'm going to talk about is generic risk assessments. So I've gone to one slide too far. Generic risk assessments, if you think about organisations that might have lots of pieces of equipment that are broadly similar, but there are different ways of using them. For example, at the university, we had lots of X-ray optics equipment. The main regulatory compliance requirements could be determined from a broad brush radiation risk assessment, but you've got to allow departments some scope to work within it. And you've got to accept that some of the assumptions you make in your overarching risk assessment might not apply to every individual piece of equipment. So we prepared generic radiation risk assessments for X-ray optics as a subject, and then allowed departments to have simpler documents that recorded specific risks and control measures related to their equipment. And the top slide there, you can see that an individual department might have a radiation risk assessment for their individual X-ray optics equipment and some simple procedures, sort of explaining how the interlocks work, how the warning lights work, and what people need to do to drive the equipment safely. And then the final one is probably the meat of the talk today, is the task-specific risk assessment. There are things that people will occasionally need to do that we're going to fall out of your main fall outside the scope of your main radiation risk assessment. So if I mention, say, our synchrotron, in our synchrotron we have, when the beam is off and people can go inside, we have risk assessments and we have local rules in place to manage the risks of exposure to the activated components. Got components in there with millisievert per hour sievert dose rates. Sorry, millisieverts per hour contact dose rates. So we have to control how people can go in and out. So we have local rules for that procedure. And therefore the routine work and for reasonably foreseeable accidents that can arise out of that routine work. But then what happens if somebody wants to refurbish something in there? What happens if somebody wants to rewire something or take out a magnet and replace it with something else? Then they could get up close and personal with some of the equipment that our routine procedures tell people to stay away from. So we have to do task-specific risk assessments. And we'll come on to those a little bit more later. When you're doing a radiation risk assessment, you only need to consider the significant risks. Don't waste your time worrying about a few microsieverts when there are much bigger hazards to consider. Don't waste your time thinking about things that are unlikely to happen. In our slide, by analogy, whilst a polar bear would do significant harm to a penguin, it would have to swim an awfully long way to get to it. Other issues might present a greater risk to a penguin, ones that are more proximal to the penguin. So I should say thank you to SeaWorld here for their information on penguin predation. It's not my specialist subject, but fortunately an online resource helped me with it. On the practicalities of doing a risk assessment, ask the questions that other people might have asked. Don't be afraid to do that. Ask about things that might not ultimately be reasonably foreseeable. On the way to dismissing that, you might identify something more likely that does present some risk. And don't be afraid to ask stupid questions. I am often the least intelligent person in the room. Really don't care about that. The most important day I had in my career at Oxford University was when I said to a scientist that they should explain something to me like I was an idiot. I'm not a boffin, but if I don't fully understand the research somebody's doing, does it actually really matter as long as I can understand the process? As long as I understand the hazards, as long as I know how radiation's generated, what happens to the material, how people come into contact with it, and what can go wrong, that's all that matters. So if when you're trying to get to the bottom of how something works, you find yourself blinded by how it's being explained to you, tell somebody to explain it to you in a way that allows you to get the information you need. So, conclusions of your risk assessment. I'm not going to go into great detail here. We can read what the regulations say about radiation risk assessment, and these are what I explained earlier as the matters to conclude. So ACOP 71 tells you what you should get out of a risk assessment, and in doing so, it tells you effectively what you need to determine to be able to say you've restricted exposure so far as reasonably practicable. But if I can mention a couple of the points on here. Dose constraints and investigation levels should be specific. An investigation level is the point where you decide that you need to stop to double check whether your procedures are achieving a LARP. So they should be specific to what it is you're doing, and so determined as an outcome of this radiation risk assessment. Similarly, contingency plans should be for the reasonably foreseeable instance. Don't just go to loss, theft, fire, failure to terminate. We're doing risk assessments at the moment for moving high activity components using cranes. So we've got risk assessments for, what happens if the crane fails? What happens if some device that you're using, an electric tug to move a very heavy flask around the site? What happens if the electric tug can't cope with the weight of the flask? All of these that are more reasonably foreseeable, we have to address, and we have to come up with contingency plans, procedures to dealing with these incidents if they happen. When we're talking about hierarchy of controls, let's just be clear what we mean here. This slide shows the ISIS accelerator engineering controls and safety features that prevent people being exposed within the accelerator vaults. The engineering controls include shielding, trap key systems, and the safety features include interlocks, beam off buttons, installed monitors, and search procedures. Now, search procedures, we say it's a safety feature. It's also a procedural control. So how this system works is that only when each of these individual items are functional and they provide the required input to the personal protection system, will the personal protection system then provide an output to what we call the beam permit system. So all of these measures have to give a signal for that system to say, okay, you can now generate beam. Our radiation risk assessment confirms that it isn't reasonably foreseeable that someone could get trapped inside the accelerator. They'd have to access without taking a captive key, or they'd have to lose the captive key while they're in there, and then somebody would have to pick it up, return it to the key exchange, turn it and put it back into the key exchange. Then the person who lost the key would have to stay inside there. They'd have to avoid the search. And then when everything was locked up and ready to go, they'd have to ignore all the multiple audible warnings. They'd have to ignore the fact that the entire area will be illuminated in blue light, and then they'd have to fail to hit an e-stop. So all of that defense in depth reassures us that it's not reasonably foreseeable that somebody can be trapped inside the accelerator during an exposure. Then we get to the point where, as is often the case, we think it's not possible to completely engineer out the risk. And if you can't engineer out the risk, you have to manage the residual risks. And you do that using procedural controls. So I mentioned the search a moment ago. The search might appear to be an engineered control that you can't work around, but if you don't do the search properly, so for example, if you walk to the back, you press your search button, you come out without checking the areas you're supposed to, the search isn't going to work properly. So it does have an element of procedural control in it. Similarly, some practices rely almost entirely on procedural control. And so, for example, open source work, the use of a shielded screen is a procedural control. Putting a lab coat on is a procedural control. So if your radiation risk assessment identifies that you need to rely on procedural controls for a LARP, they need to be documented, and they'll become written arrangements in your local rules. And since they're critical to compliance, someone needs to check they're actually being adopted. So you have your radiation protection supervisor. So bit of a recap, and then we'll move on to some specifics of task risk assessments. So the main overarching radiation risk assessment doesn't always cover everything in sufficient detail, or it can't cover everything in specific detail. So we have task specific radiation risk assessments. For example, the radiation risk assessment will cover the routine work and the reasonably foreseeables during the routine operations, and then somebody will want to go and do something else that's different. So they'll want to go in and say mend something. The local rules were never meant to address this, so you decide you've got to have a rethink. Risk assess what's planned, review the procedures, and provide, if necessary, some further written arrangements. But then what do you do with those written arrangements? Do they go into the local rules? What else happens with them? Well, in my opinion, it pretty much depends how long they're going to stay in force for. If those extra procedures are going to live forever, embed them into your main local rules. But if they're transient, have a separate set of written arrangements that refer to the main local rules. They can apply for a period of time, however long the task's going to last, and then you can archive them. And when you're doing your task-specific risk assessment, to what extent do you have to go through all of the ACOP 70 and 71 steps again? Well, at the very least, the process should determine whether the assumptions and judgments you made for your overarching risk assessment are valid during this extra work. So you should review the appropriateness of your existing control measures. But you should review it with a view to think, okay, what is different in this task? What is different to what I've already assessed and got procedures to address? So how do I do a task-specific risk assessment? Well, I've tried to put a little schematic there of some of the this isn't the entire process. This is the stuff you need to do to get it going in the first place, to get it off the ground. So you have to consider what it is you're doing. How will it be done? What are the hazards, or how will existing hazards change? Who will be doing the work and who will be affected by the work? And then what controls are there, or what controls need to be implemented during this extra task to reduce exposures. The problem with task-specific RRAs is that you sometimes struggle to get the information. Task-specific RRA is really one where you need to involve people. The people who want to do the job will know exactly how they want to do it. In my experience, the kind of people who want to do the more troublesome tasks are those who are least keen to commit the information to paper. So you probably need to badger them to write it down. If you take anything from this talk, I'll give you a catchphrase. I'm sick of myself hearing it, and it'll be good if I ever hear one of you say it in my company. And it's, you can't risk assess nothing. We're forever asked to say, can you do me a risk assessment? I want to do this. Well, I can't. Tell me what it is you want to do, because it's the task you're about to perform. That's what I'm risk assessing. So I need you to tell me that task. How are you going to do it? At STFC, we're currently planning a long shutdown to refurbish one of the target stations. The existing target station risk assessment and local rules go out the window, and an entirely new set of task risk assessments is required. We've recently convened a working group of critical people to brainstorm the tasks, so we can undertake risk assessments for the work. So we get them together and we say, how are you going to do it? What could happen? What stops it happening? What could go wrong? If it happens, what you're going to do about it? And so we've had lots of people in the room effectively talking through the process, working off each other, and just throwing considerations into the mix. As a result, the working groups effectively co-authored the radiation risk assessment, the local rules, and the contingency plans. And as a result, they now understand the basis behind the instructions they contain, the instructions they're required to follow. And so they feel ownership. Because they're involved in the process as well, they're also more likely to remember them. Personally, I think that's one of the most satisfying experiences of my professional career. To get people together to work through the process and be able to sit in front of them and say, look, effectively, you wrote this, you know why we've written this. So I would encourage others to do the same. Considerations of the task radiation risk assessment. We've sort of spoken about this. It's fairly self-explanatory. It's a review of AURPO 70 and 71 for a specific task. As before, you're considering the things that are different to the overarching radiation risk assessment, and you're really only acting on the things that change. So examples, you might need more monitoring, you might remove shielding, there might be consequences of doing things. So for example, the contingency plans, implementing a set of contingency plans in a particular way in a particular task might have consequences. And for example, we're currently looking at work involving refurbishment of an area. So there's going to be people working in personal protective equipment inside an area that's designated as a controlled area for contamination. And we're saying, OK, what happens if there's a fire alarm? How do people get out of that controlled area? They're getting out in a hurry because there's a fire, but they've also got these degowning considerations. Do they degown, or do we let them overspill to an area that's separate, that we can control and maintain on the basis of contamination? So there are those kind of task-specific things to consider. But also looking at this slide here, one of the most important things I think comes out of a task assessment is is the issue of the hold points, the action levels and the hold points. So remember that risk assessments are all about achieving a LARP, and investigation levels, action levels, hold points are all about managing whether or not we are successfully working towards a LARP. So is there a certain stage in the process where you're going to say to people, okay, let's stop and have a think? If a dose rate alarm goes off, if an airborne activity monitor alarms at you, or if an EPD beeps, what is it we do? Are we going to retire from the area and we're going to stop and rethink? So these should all be task specific action levels. And then finally, with your risk assessment, I'm going to go into some examples after this. What happens? What do you do with it? Do you just stick it on a shelf and say job done? Was it just a hoop you had to jump through to get permission to do the job? Stick it on file and get on with the real work? No, of course it wasn't. Now what we do is we give it to the workers to read, because if they read it, they'll understand all about it. But then that merges the risk assessment. When does a risk assessment stop and a procedural control start? The purpose of a risk assessment is to identify the measures to achieve a LARP. And so, as I've said a couple of times, if it identifies them that need to be managed through procedural controls, we write procedural controls. If it identifies extra engineering controls, we prepare those engineering controls. The issue about I'm just going to give my risk assessment to the workforce and get them to read it. I've written risk assessments that are a dozen pages long, full of mathematical calculations, full of considerations, and they've resulted in perhaps a couple of bullet points. Don't assume everybody wants to read the lot. Tell people about it. Tell them about the significant findings. Tell them what it identifies as the main risks. Explain them, put them into perspective. Tell people what they can do to control those risks. And so if it does identify a couple of bullet points, you write down a couple of bullet points, and they're your written arrangements for the procedure. The other thing about risk assessments is we review them. It's possible that we can get a risk assessment wrong. So if you identify something as you're going through the process that's different to how you assessed it, stop, take action, rethink. Review it at the end. Review it before you do the task next time. Risk assessments, the phrase is that they're a working document. So keep them under review. Don't just sit them on a shelf, otherwise they're not doing their job. Some examples. Life science work with open sources lends itself to task-specific risk assessments. Academic institutions will have overarching risk assessments for work with open sources that say how they're complying with the ionizing radiations regs, how they've designated their controlled areas, what they've written in their local rules. But then it's likely that an overarching risk assessment won't consider every risk during every single laboratory open source protocol across a research establishment, and some of those protocols could carry quite significant personal risks to the people undertaking the work. For example, in my time at Oxford, the quantities of PET isotopes we used in research glove boxes could result in very high skin doses from inappropriate handling or from unidentified and not quickly remedied skin contamination. So you have to address that. You have to address the fact that those risks are very dependent on the procedures that the people are carrying out. So we need to risk assess the individual procedures, and so we used readily available hazard data. You can see there on the slide I've shown you a screenshot from Delacroix, and we required researchers to carry out extremity and effective dose calculations per procedure. So they worked through their procedure, estimated the kind of doses that could result routinely or if something went wrong, and then they used that as a scaler based on the workload, i.e. every time I do this, I'm going to get a finger dose of X microsieverts and a body dose of Y microsieverts. I'm going to do that approximately this many times during the year, so my overall exposure is X. And they did it using this kind of method, where they effectively mechanically linked the process they were doing to one of the images in Delacroix, say, okay, that most resembles this. The source is presenting itself to me in this kind of situation. And they would do some kind of calculations to work out what the doses were. But that was only part of the process. That was the dose calculation. That was effectively part of the estimate of the risk. But if you look at ACOP 70 and 71, there are the other considerations. Now, to be effective, risk assessments can't be seen as a burden. They have to have a purpose, and you have to give people help. And so we created this template and guidance. You can see there on the left, there's the template, and on the right, on the back of it, there was a set of guidance, and the red is me giving you an example of how it's populated with data for a P32 procedure. Like I say, please don't try and read it. So if we made it easy, then people could follow through it. And chemists at the university were already doing experimental risk assessments before experiments, so this soon became an accepted and a beneficial step in the process of developing any new protocol. And again, the benefit of doing it was that the researcher identified and understood their own risks and the consequences that their actions had. And so they understood the protection measures, they understood the most important protection measures and how important it was to use them. I think I'm going to, I'll briefly mention this one. This is an example, a second example. This relates to some work in RISIS synchrotron. Somebody wanted to stick some vibration sensors into the synchrotron. And there you can see the vibration sensors, that grey block. It was a mounting washer was glued onto the synchrotron. The vibration sensor was then going to be screwed into it, and a cable was going to be screwed into the vibration sensor. So the task as was initially described involved 3 separate incursions into high dose rate areas. So the risk assessment process very simply, at least initially, said, why don't you join them together first and then glue them on as one? So a very practical consideration of the risk assessment process. But how did we do it? Well, here you see the part of the synchrotron. Our synchrotron is made up of 10 of these, what we call super periods, dipoles and steering and shaping magnets that guide the proton beam around the synchrotron. To do the procedure, people had to get close to these devices, these components, I should say. So the information we need is mainly dose rate information. So we got that, and then you could do a calculation based on the length of time, the proximity, and guesstimate the time of dose, the type of doses people might receive. The more eagle-eyed amongst you will see we have some very, very big numbers. So there are some of those areas where you've got tens of millisieverts per hour dose rate, so people don't want to be spending a great deal of time in there. And the other thing, there's a difference in risk assessment between a body dose and an extremity dose. So we have to factor that in. So part of the outcome of the risk assessment was stand here, don't stand there, wear an electronic personal dose meter, wear an extremity dose meter, any thinking time you have, retire to a low dose rate area, etc. And we wrote that down in procedures. The main thing we got out of this was some of the people doing this work were quite sensitive to radiation. They were concerned about radiation exposures, and getting people to wear an extremity dose meter was partly to reassure them of the fact that their doses were, even though the dose rates they were subjecting themselves were quite high, the length of time was likely that the exposures they received was going to be quite low. And so we showed them that. We calculated their extremity exposures, we measured their extremity exposures, then we showed them to them. So as part of the review of the task, as well as considering things like how did it go, could anything have gone better, do we need to change anything the next time we do it, we showed them about how to the type of exposures they got and whether they were significant. And you see there, that's from a day's incursion into the synchrotron. They were getting extremity exposures of a few microsieverts. So the exposures really were quite negligible, and we were able to reassure people. Finally, I'll give you an example of a work in progress. So I'm from STFC, so it's fairly likely that I'm going to explain to you a little bit of the significance of some of the risks that we have to consider as part of our risk assessment processes. At the moment, we're undertaking a refurbishment of one of our target stations. So here on this slide, this is the point where the accelerated 800 MeV proton beam hits the tungsten target and it creates neutrons. The neutrons are generated, reflected and moderated in the center of the image, and then they're guided down those where those arrows are to the beam lines where they go into the experimental blockhouses. The entire target assembly is being replaced. So that bit in the middle is all getting ripped out and changed. And your basic source term, the contact dose rate on the items that we're going to tear out of there, the contact dose rates are of the order of several tens of sieverts per hour. This shows an image. The bottom of this image shows you the target in position. You see there the arrow on the left talks about the operating position. The orange item is the target assembly. And that's the whole system in its operating position. Now, when we want to do any maintenance work on it, the entire assembly can be reversed backwards, you see in the top slide, such that the target goes into a remote handling facility. Now, in order to remove the target, or the target assembly, we have to roll it back, remove, dismantle it, and then drop it out of a hatch on the left hand side there, drop it out of a hatch into a tunnel beneath where there would be a recipient flask waiting for it, a very well shielded flask. That flask will then get trundled along the trolleys, along the tunnels on a trolley. It's actually an electric tug, and it will go to a point where you see on the right hand side there, there's an overhead door where it's lifted out by a crane for ultimate transfer to our waste storage facility. One problem we have as part of this process is that the point at which the crane hoists out the flask to the point where the flask has to leave the building, you can't get there as the crow flies. There isn't the clearance height to lift the slung flask directly to the loading bay. It has to take an extended route around the halls in order to get there. This is what our flasks look like. So there we have the outcome of some Monte Carlo modeling there, and there you can see some dose contours around the assembled flask. And on the right hand side there, you'll see in the top image is one of our complete flasks. Now, the problem we have is that because of the limitations of our electric tug, in terms of its load lifting capability, because of things like floor loading, because of some of the limitations of the cranes we have to use, we can't put all of the shielding on initially. So some of our initial operations have to be carried out with a partially shielded flask. And that partially shielded flask there is shown at the bottom. So aspirationally, we want to get to a point where we've got a surface dose rate of 1 millisievert per hour about these flasks, but we accept that part of our moving at the start, we have to play with things that have got a surface dose rate of 20 millisieverts per hour. And then you consider what happens when the crane picks it up. Like I say, because the slung load dangles too low and you can't lift it over the accelerator, you have to take it on an extended tour of the halls. So we've got something with a surface dose rate of 20 millisieverts per hour taking a 5-minute trip around the halls. Now the thing is, this is a contact dose rate, so let's not get too hung up on the contact dose rate. We're bothered about the dose rate at distance, and people are going to be, well, they're going to be cleared out of the halls. Essential people are going to be living in the halls, are going to be a good distance away. But there are other considerations. So leave you with this. This is my final slide. These are some of the challenges we're currently considering for this process. So we've talked about 60 sievert per hour contact dose rate. We've talked about the millisievert per hour on the outside of the flask. And so the flasks necessarily have to be very big and very heavy. The flasks aren't transport rated, so we don't want to drop these flasks, as we can't say they meet certain drop test requirements. But are we likely to drop those? Well, we say no. Lifting equipment, it is not reasonably foreseeable that it's going to fail. It's all tested and maintained, and each lifting point is rated so that it individually it has 6 to 1 greater than the weight it's required to lift. The other thing we have to bear in mind is that when this thing's taking a tour around the halls, there are other things, other risks that you might not ordinarily think about. And one of our ones that came out in a recent set of conversations is when we're taking something around the halls with 20 millisieverts per hour surface dose rate, it's going to go quite close to our stack detectors. So they're going to get a nice spike that might at some point look like we have discharged significant amount of activity into the environment. So these are the other kind of situations we have to, the other kind of scenarios we have to consider. So all in all, I've tried to provide you with a practical view on radiation risk assessment. I've tried to explain the considerations and the benefits of doing risk assessments and some of the pitfalls in doing it. Hopefully that gives you some pointers now to help you do your own. So thank you.